Swayam Prabha. Digital India. Educated India.
Hello all. So in the last class we had discussed about the simple passive strategy pertaining to form and orientation. We had seen how orientation and form are very important criteria. This time we will see about planning. There will be some overlaps between planning and a little bit on orientation might also come in, fenestration may come in, because these things are a little interlinked. They cannot be segregated completely as black and white. However, I have tried my best to keep it separate. So, we will see about planning. In this class, we will look at the passive architecture and planning strategies with reference to orientation and layout, form and massing, a little bit on fenestration, position of fenestration, density and zoning, green spaces, mixed use development, transportation planning, materials and construction, natural resource management, climate responsive design, and we will finally conclude with case study. This entire content may not be possible within one lecture, but the forthcoming lecture would also have this content. Now, bioclimatic architecture aligns with passive design principles by utilizing natural factors like neighboring structures, local biodiversity, and climate to regulate a building's temperature and energy use. Passive design relies on natural conditions, minimizing the need for artificial climate control by optimizing layout, materials, openings, and orientation for enhanced environmental comfort. Implementation of passive design not only makes individual buildings more eco-friendly, but it also contributes to a significant reduction in overall energy consumption when widely adopted. The key principles include selecting openings for sunlight in colder months and facilitating ventilation in hot climate, but at the same time optimizing the openings to ensure less solar gain. Passive design plays a crucial role in mitigating the carbon footprint of the construction industry, a significant contributor to carbon dioxide emissions. Integration of passive design strategies is pivotal in achieving net zero building by reducing energy demand and improving indoor environmental quality. If we look at bioclimatic performance, the passive design aligns with the principles of bioclimatic architecture, which lies in utilizing natural conditions to regulate a building's temperature and energy use. This fundamentally involves considering the contextual factors surrounding a building, such as neighboring structures, local biodiversity, and climate. Utilization of natural conditions pertain to passive design as an approach that relies on harnessing natural conditions to minimize the reliance on artificial or mechanical climate control. This involves optimizing a building's layout, materials, openings, and orientation to maximize the benefits of natural elements, ultimately enhancing environmental comfort. Reduced energy consumption. The implementation of these strategies not only enhances the environmental friendliness of individual buildings, but also leads to a significant reduction in overall energy consumption when widely adopted. Fundamental principles of passive design include the selection of openings that allow sunlight to enter during colder months and facilitate ventilation during the warmer months. It also entails mitigating carbon footprint, given that the construction industry is a notable contributor to carbon dioxide emissions, with raw material production accounting for a substantial portion. Passive design strategies play a very crucial role in reducing these emissions and contributing to a lower carbon footprint, because you are not actually adding anything to the design. You are only prudently using what is there on the site with a keen understanding what is there around the site and trying to design a net zero building. In net zero building, a pivotal aspect involves the integration of passive design strategies to decrease energy demand and enhance indoor environmental quality. So, now the configuration and pattern of massing in the built form can largely determine and modify the air movement both inside the buildings and around the buildings. Depending on the relationship between the wind direction and that of streets and buildings, there may be variations in wind speed. When large built volumes, or say a long row of buildings, are placed perpendicular to the wind direction, then shielded zones are established between the buildings, where wind speed might be just a small fraction of the speed above the building's roof, or in streets parallel to the wind direction. In this case, the distance between the buildings have little effect on the speed currents between the buildings. The first row of buildings divert and approach wind currents upwards. The rest of the buildings are left in wind shadow regions. Thus, two separate airflow regimes are created. The regional air currents flow mainly over the top of the buildings, while in between the buildings a secondary airflow pattern is created as a result of the friction between the upper air currents and the building. This may be desirable in certain climatic conditions like the cold winters or hot summers, when winds are to be avoided, but undesirable in warm humid climate when ventilation is required. On the other hand, when building blocks are placed parallel to the prevailing wind direction, the wind can blow through spaces between the buildings and along the streets with small retarding effect from the friction with the buildings. In this case, the interior of the buildings suffer from poor ventilation, while the adjacent open spaces experience high wind velocities. Orienting buildings at an angle in relation to the wind direction can produce relatively homogeneous wind patterns around them, thus creating better ventilation regardless of the relative position of buildings within the built-up arrangement. Now, solar radiation, the we have to plan buildings to take advantage of the natural sunlight. The key points here which we have to understand is we need to maximize exposure of the sun in cold climates. We need to reduce solar heat gain in hot climates. Energy efficient use of sunlight reduces reliance on artificial lighting and heating, while proper solar orientation enhances occupant comfort. We need to take care to ensure that we orient structures to maximize exposure to the sun in cold climates or reduce the solar heat gain in hot climates while reducing the need for artificial lighting and heating. The considerations we must have when we design for wind patterns, that the prevailing wind patterns for optimal natural ventilation must be tapped. We must improve indoor air quality with fresh air intake with natural cross ventilation. We should also reduce the reliance on mechanical ventilation system. Therefore, with wind patterns, we must consider prevailing wind patterns when placing buildings to optimize natural ventilation. This helps improve indoor air quality and reduces the reliance on mechanical ventilation systems. It also the effect of massing on wind, staggered versus not staggered layout. The staggered clustering has a better wind performance without dead wind zones. What I mean by this is staggering the building. Once the buildings, if they are staggered, the wind seamlessly flows around it and hence all the rooms get the benefit of its ventilation. When the buildings are not staggered but they are in file, it causes a small wind shadow region. Now, when we have too compressed street pattern, it results in air movement at a higher height. Winds are placed on less compressed areas. With more spacing, when you have very less space in between the buildings, as shown here, it results excuse me in the air movement over the buildings. Percolation does not happen, whereas if you have wider spaces between the buildings, then the wind is dragged to the bottom in the open spaces than that are potentially uncomfortable. This is intensified by tall buildings and tornadoes are appeared. Tornadoes are, here we mean very small tornadoes, also resulting in heat loss. Building form also affects the quality of open spaces due to channelizing the wind in the street. So, having